So the big question is, how do I know if my problem is suitable for a dynamic programming solution? There are two ingredients to a good dynamic programming problem. The first is what's called optimal substructure. This means the problem's optimal solution contains optimal solutions to subproblems. What does this mean? Let's take the rod cutting example. Let's suppose that the optimal solution looks something like this. We're going to have, let's see here, a rod, and we're going to have some cuts. And let's consider this cut here. What optimal substructure means is either side of this cut is an optimal solution. So this is an optimal solution for length n. And this is an optimal solution for length m. So suppose that we have some other optimal solution of some other rod. Let's say it's that long. And let's suppose there's a cut right there. And let's suppose that this piece right here is length n. Then the optimal solution must be identical to that solution there. So anytime you have a rod of length n, given some n, so anytime you have a rod of length 4, its optimal solution is always going to be the same. In the homework, you'll see some problems that might appear to have optimal substructure but don't. Let's take another example, sequence alignment. As we showed, sequence alignment is well suited to dynamic programming. A, T, G, G, C, G, T, A, G, G. Now, let's say I is here at the A and J is here at the G. Now, how could we have gotten to this point? Well, we might have done a match and then an insertion and then another match. And that could get us to where we're at. And what we're trying to do now is solve this subproblem. GC on the top, AGG on the bottom. Now, let's suppose we have some other, let's take the same sequence. A, T, G, G, C, G, T, A, G, G. And we have I and J in the same place. And so we're trying to solve the same subproblem. But let's suppose we got there a different way. We first maybe did an insertion, and then we did 2 matches. And so the solution to this problem and this problem are different. We don't know which one is optimal, maybe. But the solution to the subproblem, the red subproblem, this right here and this right here, matches. Same solution, same optimal solution, even though we got to this point different ways. Okay, so that is the first ingredient for dynamic programming is optimal substructure. The second ingredient is overlapping subproblems. So let's do the rod cutting example again. We have a rod, and according to the algorithm, we're going to make a cut of size 1. Then we'll solve the subproblem of size n minus 1. Okay. Then we'll make a recursive call, and we'll cut another one of size 1, so now we have 2 here, 2 of size 1 each. We have n minus 2. And we're going to solve this problem with size n minus 2. Now, another branch we're going to take down the tree is we're going to go directly to cutting a rod of size 2 off the front, and we will solve the subproblem of size n over 2. Notice these two are the same subproblem. And that's what we mean by overlapping subproblems. We're going to go down through the recursion tree, and we're going to encounter the same problems over and over and over. And you can see why memoization or dynamic programming would help with that, because we're simply going to remember what the solution was, what the optimal solution was to a given subproblem.